The nomenclature for cycloalkanes is very similar to the alkanes that we have done. There's just some differences, okay? And then there we're also going to do bicyclics in here, which means more than one ring, but joined in a little bit different way, okay? So yeah, a little different. All right, so first of all, little intro over here about the basic ring structure. So cyclo, of course, as soon as you put cyclo in something, it means it's a ring structure. The smallest ring you can have is a triangle, right? So you need at least 3 carbons for this one. The general formula of a ring is CnH2n, which is similar to alkene, which means that from alkanes, the cycloalkanes are 2 hydrogens less, okay? Because remember, the alkane formula is CnH2n plus 2, and then cycloalkane is CnH2n, so 2 hydrogens are lost, okay? In this case, in forming a ring, okay? Because you're forming a bond now, right? And so you have to lose something, and here we lost hydrogens. Okay. The base name or the parent name of the name of the compound is going to be the cycloalkane in general, because in some cases where there is a really long chain attached to the cycloalkane, then the long chain is the parent name. Now, that's generally the basis for deciding how do you name something. So for example, if you had a 3 carbon chain here, a 3 carbon ring here, and then a long chain, how is it easy for you to name this compound? You can name it giving this the base name and this as a substituent, right? So this is easy to do, and this is the right way also to do things because these are more number of carbons. So the more number of carbons you have in a chain or in the ring, that gets the preference to be the base name. Okay, that's how it goes. Okay, then you also have to number the carbons if there is more than one substituent. If there is only one, you don't have to. Okay, that's the nice thing about cyclic compounds. And then, of course, here the numbering. Remember how we talked about it? If you have 2 substituents in there, you give the lower number to the lower alphabet substituent. Okay, it's not about the size, it's about the alphabetization. So first of all, these are the rings that we are dealing with most of the time, and those are the cyclopropane, cyclobutane, cyclopentane, cyclohexane. I will tell you something. This is a really weird thing that happens when you start drawing rings. Sometimes we just don't see the ring. And I know you're probably thinking, how could you not see the ring? I don't know what happens. I have no idea, okay? But a lot of times I will give this, okay, and I will get hexane as the name, not the cyclohexane. Okay, so we don't even see the ring or we forget the name cyclo. I don't know what happens, but pay attention, okay? As you're doing the nomenclature, just be aware, self-aware. So here are some names, and again, I don't have to go through the rules all the time, so you know the basic rules. Those are the fundamentals. So right here, this one is methylcyclane, cyclohexane. This one, the base name is cyclopentane, so cyclopentane. And then on the first carbon, you have the ethyl, and you also have methyl. So because you have 2 substituents, now you have to number them. Okay, give the locant for both of them. For if it was just one, you don't have to, because that methyl could be here, 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 it'll still be the same thing. Here where you have 2 substituents, so where you have a choice of where do you start numbering, start with the ethyl group because that's alphabetically lower. So chronologically and alphabetically we will be happy, okay, in cyclic compounds. So that's how we write this one. Again, don't forget the dashes and such, okay? And here I have given you a comma example also where you have 3 substituents now. And in this case, you can see that I did not start with ethyl group. Okay, I did not start with the ethyl group because everything should have the lowest number of substituents as much as possible. Okay, so 1, 2 is going to be lower than 1, 2, 3, 3, 4. Okay, so you have to give the lower numbers, all right, for all the substituents. That's why this is numbered the way it is numbered. Okay, here we have two of these cyclopropanes over here. But what happens here is that we have this long chain in the middle. So butane is our base. Butane is our base or parent name. And then on the first carbon and on the fourth carbon, you have the cyclopropane ring structure, but the cyclopropane is not going to be cyclopropane because it is attached to something, so -1 hydrogen, which means that it's going to end in -il. Okay, so 1,4-dicyclopropyl butane. Okay, so here things are a little bit different. Here you have a cyclohexane and a cyclopentane. These two rings are bigger than the chain that we have. The chain is only 3 carbons, but because it's going to be really awkward for us to name this, it's like, how do I even start naming this? I mean, I can, okay, we can name this another way, and you should try it and show it to me if you want to. You can name it, but the easier would be to just call this cyclohexyl and this one cyclopentyl. That's it. Okay, so again, put them alphabetically. The cyclo is not part of the alphabetical, and even if it was, cyclo is still cyclo. So I mean, both of them have that. So you still have to go up till H and P in order to alphabetize them. Okay, so one cyclohexyl, cyclopentane, pentyl, propane. So there are two things that go on over here that I want to kind of just mention to you. Two things or one thing, I don't know. Anyway, when you have a cyclopropane or a cyclohexane, to make it a substituent, just remove the ane and put the -il. Okay, that's it. All right, in there. And I guess the second thing I would like to mention here with these two examples that I gave you here is, we are, bending the rules a little bit for this one, for example. So so long you're not really bending the rules completely to just fit whatever your thinking is, if it's the correct thing to do, it's fine. I will accept the name. All right. In cyclic compounds, we tend to have a little bit of a problem, okay? And that problem is that in a ring structure, you cannot rotate the bonds, okay? So we've talked about this before when we talked about constitutional isomers, is that, whether you draw a group up or down, it doesn't matter. So here, there, I mentioned to you, if you draw it like this, or if you draw it like this, it doesn't matter. I mean, this just looks awkward, but otherwise it's the same thing because you have two methyl coming out of this carbon, right? One methyl here and one methyl here. So the same thing here, one methyl here, one methyl is the same thing because this carbon, this can rotate. This carbon can rotate around, okay? So if it is able to rotate around, then it doesn't really matter, okay, that you have two methyl groups, because they will, so long the attachment is correct, right? So connectivity, as I said before. Here also that connectivity matters, okay, in the cyclic compound. The only thing about a ring structure is that you cannot rotate a ring. I mean, you can rotate the ring as in you can completely rotate it, but you cannot rotate just this one single bond, because if you rotate this one single bond, you will end up breaking it. Okay, so you can't rotate it. So if you can't rotate it, it means what? That the groups that you have on here, they are stuck the way they are. Okay, so you will see that, and I hope you form a model and you see this, is when you have two of the methyl groups going in the same direction, and this here, the dash, this line, the dash line, this means going back, and the wedges, these ones, means that coming to the front, out of the plane. Okay, so or in the same direction. Okay, so if the CH3s are going back and the hydrogens are coming the front, if you wanted one of the CH3s to come to the front, you literally will have to break the bond. Okay, so either you break this bond or you just break the CH3 bond and then you switch out the carbon and the hydrogen. Okay, so which means that these kind of groups, they are stuck in their place. If they are going to be stuck in their place, we have to be able to tell them apart. And the way we tell them apart is by cis and trans isomers. So the cis and trans isomers actually have to do with hydrogen. If you don't have two hydrogens on the compound, you don't have cis or trans compounds, which we will study differently. Is like, what do we have then? Okay, so we will do that separately, but not right now. So here the cis means that you have your two hydrogens going in the same direction. Trans means when the hydrogens are going in the opposite directions. Okay, and so here when you have the two methyl groups, so this is 1,2-dimethyl cyclopentane. So the 1,2-dimethyl means that those two methyl groups are in a very particular location because they're going in the same direction. Just like the hydrogens are going in the same direction, they're going cis. Okay, so here you can see that I've given you the model. So here, look at them, they're going in the same direction, and this one is for trans, and you can see that these are going in opposite directions. Okay, and there's nothing we can do about this. This is just the nature of the molecule, as in the connectivity, right? I mean, I talk about connectivity all the time, so this is the connectivity. So unless you are given this dash lines and the wedges, you cannot tell whether you have a cis or a trans. Okay, so for example, if I just give you something like this, a cyclohexane with two methyl groups coming out, you don't know what the relationship is. So at this point, this is just going to be 1,2-dimethyl cyclohexane. But as soon as I say, okay, this is what you have now, you have a cis relationship. Okay, over here. So you have to kind of look for these things. Another way of drawing all of these out, okay, and sometimes we do this, is like this. So for example, if you were drawing cyclopentane and let's say it was a 1,3, this is a 1,2 relationship, right? So we could draw it like this. Even with a 1,2, sometimes we draw it like this. Okay, so as soon as you draw it like this, it means it's going in opposite direction. Now, that's not my preference. My preference is this. Okay, because you can never go wrong with your communication if you draw it like this. Sometimes people have a really funky way of drawing stuff, you know, so it's like I don't want to start guessing what this is unless it's clear, okay, because sometimes we draw things in weird ways. But a dash line and a wedge line will never go wrong. Okay, so try and do that if you can for cis and trans isomers. Okay, now cis and trans, we did not have that in the alkane and the straight chain because again straight chains are completely rotated. Okay, so each bond can be rotated around, so we don't have those kind of issues, but in cyclic compounds we have. All right, so here are some problems to go through, and I don't know if I need to go over any of these. I'm sure you can figure it out. And I think I did mention this in the first one, or maybe I did not in the alkane, but the butyl and the methyl, the T is not part of the alphabetization. Okay, I think it's there, I didn't mention it. But isopropyl, the I is part of alphabetization, but in isobutyl, the I is not part of alphabetization. I know, can we confuse you more? Sure, you know, all the time. Okay, so, but in T-butyl, definitely T is not part of the alphabetization, so butyl comes first and then the methyl. Okay, so again, in all of these, I have not given you the relationship between the two, so you don't know whether this is cis or trans, so you don't have to write that out. Okay, so let me know if you have any questions in any of this. So bicyclic compounds. Okay, so when we talk about bicyclic compounds, these are going to be two rings that are fused together. So like fused together meaning that you have two bonds next to each other like this. Okay, this is called fusion. When you have two carbons connected to each other, this is kind of just like this. Okay, this is very simple. This is cyclohexyl, cyclohexane, that's all. Okay, but this is fusion, and you can see that there are two bonds that are two carbons connected to the other two carbons of another ring. This is ring fusion. Okay, so two very different kinds of connectivity here. The first one is a bicyclic compound, the second one is not. Okay, so be aware of that. So in bicyclic compounds, there are two kinds of carbons. Again, this is color coded here, so hopefully that will help you. So there is a bridgehead carbon, which is this one and this one, the red one. And then there are the bridging carbons, which are the bridges. Okay, so think of it as that you're crossing a river. Okay, and if you're crossing a river, then you have bridges on it. Okay, so here is the river going away, happy, happy. You have to get to downtown from here. There is another point of location. Your house is here, and here is your office or school, whatever. And there are three ways for you to go. These are the bridges, right? These are the bridges for you to go from point 1 to point B, or point A to point B. And so that office and your home, those are the bridgehead carbons, and the bridges are again the bridging carbons. Okay, that's how we identify these two different carbons. Generally, the bridgehead carbons, you can see, are going to be the one that have three carbons coming out of it. Do you see that? Do you see that? Do you see that? Yeah. Okay. So that's how we know it's a bridgehead carbon. Now, what I've shown you here, okay, is all the different drawings possible for one bicyclic compound. Okay, so this is, of course, all the carbons that are shown there. This is the line structure. This is another line structure. This is actually the true 3D representation. So if you were to actually make a model of this, real model, take ball and sticks, make some models out of it, this is what you will see. And here is the ball and stick model. Okay, I will give you the link for this website. Okay, it's a really good website that you can use to make structures and view them in 3D. Okay, so that's where I made these structures also. So I'll give it I'll give that in the link somewhere so you can do this. So here is your ring structure, and then here is this carbon, which is this one. Okay, kind of sticking out there. That's this carbon right here. So the 3D looks very different than what a 2D would look like, okay, for us. So just different ways of drawing. Which one do I prefer? Anyone? I know you were thinking about that question. All right, how to name all of these compounds. Now, bicyclic nomenclature is actually not that hard to do, because the first thing you have to do is count the total number of carbons in the ring. Total. So here in the compound that we had before, count the total number of carbons, and you had 6 in the big ring, and then you had the 7th carbon hanging out there, which is also part of the bridge, right? So you have to count all the bridgehead and the bridging carbons together, and that gives you the parent name. Okay, so the parent name is 7 carbon, which is heptane. Okay, that's the parent carbon. Once you know it's a bicyclo, you have to give that name. Okay, so two things are already done for you really quickly, bicyclo and heptane. Now we have to figure out what the heck this is. Any bicyclic compound is going to have 2 bridgehead carbons. Any bicyclic compound. Now we're not doing tricyclic, okay, so just bicyclic. Any bicyclic compound is going to have 2 bridgehead carbons. So now what we do is we count the blue numbers as the bridging carbons, okay, that we have. So 1, 2 on this bridge, 1, 2 on this bridge, and then 1 on this bridge. That's the blue numbers, okay? Those are the bridging carbons, okay? So you have 2 bridges here, you have 2 carbon bridge here, and you have a 1 carbon bridge in the middle. So you have 2, 1, 2. That's how it's going. Now all you have to do is put those bridging carbons right here in decreasing chronological order. I know, rules. And do you see the dot here? Okay, so 2.2.1. In square brackets, not, okay, parentheses, I think this is what you call, right? Parentheses. I call both brackets anyway. So this is square brackets, this is round brackets as far as I'm concerned. All right, so put them in square brackets, so 2 to 1. So bicyclo 2 to 1 heptane. And if you think that's it, yep, that's it. Okay, there's nothing much more to it. So that's a bicyclic compound for you. Now, if you have a substituent in there, that's when the problem is a little bit, because now some of the rules change. because until now what we have learned in naming substituents is you have to give it the lowest number. And here it doesn't work out the same way. Okay, so here what you have to do is you have to number the largest chain first before you can actually number the smaller ring. Okay, so find the biggest ring first. Okay, so here let me show you, okay, in this one, because it's easier to see in this one. So here is your bigger ring, 6 carbon. If you just look at this one, let me highlight it for you. This one is only a 5-membered ring. Okay, and you can probably see this one is also just a 5-membered ring. But the blue one, that is the 6-membered ring. So you have to number that first. Okay, once you number that, then you start finding out where your substituent is. So in this case, the biggest ring is right here. So I've numbered it blue for you, and the substituent is on the 7th carbon. So because it's on the 7th carbon, sadly, it will get the highest name. And I think I have it wrong here. It should be 7. Not, this is fine. This should be 7. Okay, so 7 methyl, and then 1, 2, 3, 3. Okay. Why am I have it wrong? Oh my God, I have everything wrong in this one. I need to fix that. Okay, so 1, and then this is going to be heptane. Okay, so in the video is going to be different than in the PowerPoint. Okay, so 321, 311 heptane. Okay, that's how this one is going to be. So just a little bit different, right, from when you have substituents in the other compounds. Okay, so here are some solved problems. Now, drawing bicyclic compounds. Okay, so look, if you look at this one, bicyclo-3,2,0 heptane, how we've done this, drawing it out is actually quite easy. Okay, this is not that hard at all. So when you know it's a bicyclic compound and you have 3,2,0, so this is how I start my compound. Is I have 3 carbons. So this is my bridgehead. This is my bridgehead. So 2 bridgehead always. So here I have 3, 1, 2, 3 carbons, then 2 carbons, 2 carbons, and then 0 carbons, 0 carbons. Okay, that's it. You don't even have to count the total number of carbons because they should come out to be right. So 1, 2, 3, 4, 5, 6, 7. Okay, they will come out right. So it will come out to be heptane. So long your bridging are fine. Okay. Anyhow, the other ones are pretty straightforward. I think, you know, 1 ethyl, 2 methyl, cis 1, 2. So cis 1, 2. But anyhow, straightforward enough. And then here also I have some things that are going to be right or wrong. So go through that and then let me know if you have any problems. Should not be any issues. And if you're wondering, by the way, just in case you're wondering, do I have to put dashes between the square brackets and the name? No, you don't have to. Okay, it's only when you have the parentheses, okay, or the round brackets. Okay, that's it, I think.